Hello. Okay, so let's start by reviewing the Perron theorem regarding positive matrices. So those are matrices with the strictly positive elements, and we have shown like a number of properties. They have a strictly positive spectral radius, and more importantly, the spectral radius is an eigenvalue. In other words, that you can solve basically this eigenequation. You find that basically the spectral radius is not just the maximum magnitude for an eigenvalue. It is itself an eigenvalue, and the associated eigenvector can be chosen to be strictly positive. I say here can be chosen to be strictly positive because we know a property of eigenvectors. Eigenvectors can be multiplied by any non-zero complex constant, and they are still valid eigenvectors, right? So for example, if you multiply, you may choose beta to be to contain positive elements, but then you may choose to multiply both sides by -1, and minus beta will also be a valid eigenvector. So when I say that it can be chosen to have strictly positive components, because of this, you can take it and then multiply it by any non-zero complex number, and you still get a valid eigenvector. But you can get an eigenvector for rho of A and make all its elements strictly positive. Okay? And then there is also, because if A has those properties, then its a transpose also has these properties. Okay, so you can apply the same idea to A transpose. And if we say that the corresponding eigenvector, positive eigenvector is beta, then you can take the transpose of both sides and get that pi A is equal rho of A pi. So you can also find a vector, a row vector, to be multiplied by the matrix from the left that gives you rho A times the vector, and this vector has strictly positive components. So the inequalities here involving vectors and matrices are all component-wise or element-wise. Now, if the magnitude of lambda is rho of A, so if I tell you that this matrix A, the positive matrix, has a lambda with a magnitude that is equal to rho of A, then actually lambda is equal to rho of A. And then the last thing we did last time was to show that rho of A is a simple eigenvalue, which means that the geometric multiplicity is 1 and the algebraic multiplicity is 1. So before finishing this topic and moving to convexity, what happens, because sometimes like, you deal with matrices, like suppose that your matrix is a matrix of probabilities, but some of those probabilities are exactly equal to 0. So what happens if the matrix contains zeros? Well, if the matrix contains zeros, it turns out that things will depend on how those zeros are located inside the matrix. So this was the genius of Frobenius. So Frobenius basically, he discovered that, if the zeros are they obey a certain pattern, then actually we preserve all those properties I talked about except one. But if the zeros are general, okay, then the only property that is preserved is this, okay, that rho of A is an eigenvalue. Okay, so generally, this is for a general matrix with positive elements and zero elements. So all elements are non-negative and there are zeros, somewhere in the matrix. Rho of A remains an eigenvalue. Now it can be equal to 0. Okay. Remember that we proved that rho of A is strictly positive last time by basically taking the trace of the matrix and showing that if you assume that rho of A is 0, you get a contradiction. But this is no longer a valid proof here because the matrix actually may have zeros. It may have zeros along the main diagonal. So rho of A can be 0, and we can find an eigenvector corresponding to rho of A. This eigenvector now is not strictly positive. It is a non-negative eigenvector. Okay, so if for a general matrix for a general non-negative matrix, what you can say is that rho of A, it can possibly be 0, and it is an eigenvalue, okay? And you can find an associated eigenvector that is non-negative. That's it. Okay, so these are the things that you can say with certainty. Okay, and I will go very quickly through the proof. The proof is basically using analysis, and the trick is to construct a sequence of matrices. Okay, a sequence of positive matrices that converge to matrix A, to non-negative matrix A. Okay, so you can take matrix A, which may have zeros, and then you add 1 plus V, 1 over V, where V is a natural number. Now, as V increases, basically this extra term decreases. But the idea is that the zeros in matrix A will be added to 1 over V. And so AV is a positive matrix. So AV defined as such is strictly positive. And so we have all the properties that I talked about in the previous lecture. Okay, so matrix AV, it has a Perron root, which is the spectral radius, and an associated strictly positive eigenvector beta V. Okay, because of this trick here. And you can choose the eigenvectors to basically so that the sum of the elements in the eigenvector is 1. Okay, so you can choose an eigenvector. Again, you can do any scaling of the eigenvector so long as you do not multiply it by 0. And so you can choose basically to have all the eigenvectors corresponding to A1, A2, and so on, to have an L1 norm that is equal to 1, which just means in our case here that the sum of the elements of the vector are 1. Now, because this sequence is a bounded sequence, right? So basically the L1 norm it's always 1 for any member in the sequence. So this is a bounded sequence. So by the Bolzano-Weierstrass theorem, we know that if we have any bounded sequence in a finite dimensional space, you are guaranteed to find the subsequence that is converging. Okay? So again, what I'm doing here, I am constructing a sequence of matrices. You know, what we know is that we are sure about this. We are sure that AV converges to A as V converges to infinity. AV is a strictly positive matrix. So you can find an associated sequence of strictly positive eigenvectors corresponding to the spectral radii of matrices AV. Now, for the sequence beta V, I don't know whether it's converging or not. There are no guarantees. We know that the A converges, but you know this does not necessarily mean that the sequence of the beta vectors will converge. But what we are sure of, because the beta vectors are bounded and they live in a finite dimensional space, we are sure of by the Bolzano-Weierstrass theorem that there is a subsequence, okay, such that basically this limit exists. So the limit beta vk as k tends to infinity exists. Okay, and then basically if the limit exists, so each element in a beta vector is strictly positive. So if you study element-wise, if you have a sequence of positive numbers and it's converging, it converges to either a positive number or 0 at worst. Okay, and so basically this subsequence will converge to a limit, and this limit, it can never be negative. So we get a non-negative vector as a limit. Okay, and then you can continue the argument. The argument again is like sort of analysis. You are basically doing limits and so on, and you will lose basically your eigenvector being positive. What we have here is just that the eigenvector is non-negative, and every other property I talked about in the previous lecture again is possibly lost. Primitive matrices. So the zeros can be inside the matrix in such a way that everything I said is true. Okay, so this happens if we have a primitive matrix. So a primitive matrix is a non-negative matrix, so it may contain zeros, but it contains zeros in such a way that there exists k such that a to the power k is strictly positive. In other words, that the zeros may be inside the matrix, okay, but perhaps if you raise the matrix to the power 3 or 7, you get a matrix with a strictly positive elements. If your matrix has this property, it's called the primitive matrix, and it turns out, and you find like a page on this in the notes, that actually all the properties of the previous lecture holds. So despite the fact that the matrix itself may contain zeros, but if we can find the power of the matrix such that a to the k is strictly positive, everything is preserved. Okay, and the keys, I mean, I will leave the details, for you if you are interested to read from the notes, but the idea here is based simply on the fact that if matrix A has eigenvalues lambda 1, lambda 2, and so on, then a to the power k has the eigenvalues lambda 1 to the k, lambda 2 to the k. So basically, the eigenvalues of the power of a matrix are related directly to the eigenvalues of a matrix. Okay, and so you can exploit this relationship to show that if your matrix A contains zeros, but for some power a to the k is strictly positive, then you are good, and everything basically holds. Then there are irreducible non-negative matrices. So irreducible non-negative matrices, this is like sort of a generalization of primitive matrices. So any matrix that is irreducible and non-negative, every matrix that is primitive, it is also irreducible and non-negative. The converse is not always true. Okay, so the irreducible non-negative matrices, they include the primitive matrices as a special case. So what is the difference? What is an irreducible non-negative matrix? It is a matrix such that for every entry, there is a power of the matrix such that the entry is strictly positive. So see the difference between primitive and irreducible non-negative. For primitive matrices, there is a single power. Let's say that k is equal to 7, such that a to the power 7 is strictly positive. All the elements in a to the power 7 will be strictly positive. Now for irreducible non-negative matrices, for each entry, for each element in the matrix, there exists a power, and you can show that this power will be from 1 to n minus 1, such that the ij element in a to the power k is strictly positive. So basically, if you raise the matrix to the power 7, it may be that element 3, 4 is strictly positive, but not other elements. But the other elements, they will be strictly positive for some power. Okay, so that's the reason that primitive matrices are special cases of irreducible non-negative matrices. So it was Frobenius who proved that for irreducible non-negative matrices, everything that I said in the previous lecture holds, except one thing. So basically, for those matrices, rho of A, rho of A is positive. For rho of A, there is an associated eigenvector that is strictly positive, and so on and so forth. What is missing is basically this property. So this property that if I tell you that there is an eigenvalue with a magnitude that is equal to rho of A, if your matrix is positive, or if it is primitive, then you are sure that lambda itself is equal to rho of A. Now, for a non-negative irreducible matrix that is imprimitive, so that is not primitive, then there, basically magnitude lambda equals rho of A does not imply that lambda is equal to rho of A. So this is the lost property. So if your matrix is non-negative irreducible and it is not primitive, then again everything holds except this property. So this is an example of a matrix that is non-negative and it's irreducible. okay, you can check that, basically if you raise this matrix to some power, basically, so for example, if this matrix is raised to the power 1, those two elements are strictly positive. Let's actually square this matrix. So if we square this matrix, 0 times 0, 1, 1, so you get 1, 0, 0, 1, right? So basically elements 1, 2, and 2, 1 are strictly positive in a to the power 1, and elements 1, 1, and 2, 2 are strictly positive in a squared. So that's basically, matrix A is a non-negative irreducible matrix, because for each element you can find the power such that the power is basically for such a power the element is strictly positive. It's not necessary that all elements are basically positive, and so basically this is an example of a non-negative irreducible matrix that is not primitive. Because if A cubed will be the matrix itself, and so on. So basically there is no power such that there is no power k such that a to the power k has strictly positive elements everywhere. No. But what you can say is that each location in the matrix can be made strictly positive by raising the matrix to some power. Okay, so this is an example, and if you do eigen decomposition to this matrix, you will find basically that rho of A is equal to 1. The matrix has two eigenvalues, -1 and +1. So there is an eigenvalue, so we have lambda equals -1 with magnitude lambda equals rho of A, but lambda is not rho of A. Okay, so we lose this property for non-negative irreducible in primitive matrices. If our non-negative irreducible matrix is primitive, everything holds. Okay, and what if our matrix is not irreducible? Well, this is the least we can say. That rho of A is an eigenvector. Rho of A is an eigenvalue, and the associated eigenvector can be made to have all its elements non-negative. Okay, so you may have zeros in there. Okay, so this is the story of zeros in the matrix, and again, it was like it turns out that how the zeros enter into the matrix will basically dictate whether the Perron theorem will be still obeyed or not. Okay, for irreducible matrices, I think I will send you like references if you are interested. They are very nice, and we will encounter them again in Markov chains, because Markov chains are characterized by transition probability matrices, and sometimes those matrices have probabilities that that are equal to 0. Okay, and so this concept will we will come back to it again. Okay, so this is the Perron Frobenius theorem, and now I will move to the chapter on convexity. Any questions? Okay. So basically, before going to some theorems regarding convex functions and convex sets, you started to talk about convexity in the first tutorial session, and I would like emphasize something that you said and give an example. So there was this function phi, which basically is, so you have a function defined on a certain domain, which is a subset of Rn, say, and basically this function is convex if and only if phi of lambda, which is defined in such a way, g of lambda x plus 1 minus lambda y, is convex for every x and y that is in the domain of the function, and lambda is living between 0 and 1. So never underestimate this property here, because the phi function is a function of just a single variable. It's a function of lambda, which is a scalar. And so checking the convexity of this function is relatively easy. For example, if the function is twice differentiable, you just differentiate it twice and check that your second derivative is non-negative. While this function, typically it's a function of n variables, and if you want to use basically differentiation to investigate whether the function is convex or not, then you need to construct the Hessian matrix and then basically investigate whether the Hessian matrix is non-negative or not. So basically it's a difficult process. But dealing with that function phi in many cases is straightforward, and you can use it actually to show the convexity of some difficult functions of several or many variables. Okay, so I would like to highlight this property here and give you like an example that is very relevant. It's the log determinant function. It's a very useful function that appears in information theory. Okay, so appears in information theory because it's related to the differential entropy of Gaussian vectors. Okay, and since we are talking about Gaussian and we are talking about information theory, then if you are doing communications, then this function will appear a lot. Okay, because actually the channel capacity formula for MIMO channels in which like you employ multiple antennas, it has this log determinant function. Okay, so it's very important, like basically to understand this function and basically show now that it is a concave function. Okay, so again, the log det function is not just a curiosity. I mean, we will make a big use for it, especially if you're taking with me the wireless course. Okay, so what are our variables? They are living inside the matrix X, and matrix X is Hermitian, positive definite, and again we are taking its determinant, and since the matrix is Hermitian and positive definite, the determinant is a strictly positive real number, and so you can take its logarithm, and this is our function, the log of the determinant of X. Now, so basically this is a function of how many variables. Basically the variables are the elements of the matrix. Note that basically the matrix is Hermitian, so basically element ij for I not equal to j is the complex conjugate of element ji. So we do not have exactly like n squared variables, but we have so many of them. And so let's basically try to use this trick here to show that the log determinant function is actually a concave function. Okay, so I will define function phi of lambda. So again, it is you take the function log determinant, and then you have log determinant lambda x plus 1 minus lambda y. X itself is a Hermitian positive definite matrix, y is the same, and lambda is between 0 and 1. And to basically get something that depends on lambda, we need x not to be equal to y. Right? If x is equal to y, then basically lambda x plus 1 minus lambda x plus 1 minus lambda x will just be x itself, and we don't have lambda. Okay, so for this thing to be a non-trivial function of lambda, we have x not equal to y. Okay, so this is our function. Let's start manipulating it. And let's just rewrite this as y. So we have a 1 times y here, so it's y, and then there is a lambda and lambda x, okay, and minus lambda y, so we have this thing. Note that the matrices are positive definite, so both of them are invertible, and you can define a square root for the matrix. You can define y to the 1/2 or y to the -1/2, okay, using the eigen decomposition, right? So if y is q y lambda y q y Hermitian, then basically y to the power 1/2 is simply that you go to this matrix of eigenvalues and you take the square roots of the eigenvalues, okay? And y to the -1/2 means basically the same matrix, but you take the reciprocals of the square roots. And those operations are well defined and valid because the eigenvalues are real valued and strictly positive. Okay, so what you do is that you split this y to y to the 1/2, y to the 1/2. You can check easily that this product will restore y, and you take y as a common, y to the 1/2 as a common factor to both the left and the right. So you end up here with identity, and here basically you have a lambda x minus y to compensate for this common factor. Now you put here y to the -1/2, and you put here y to the -1/2, and again you can check that y to the power -1/2 times y to the power 1/2 gives you identity. Okay, then we know that the determinant of gamma phi is the same as determinant phi, is the same as determinant gamma multiplied by the determinant phi. Okay, so basically you have the determinant of three things multiplied together, so you can basically separate the terms and as a product, and then you have a logarithm here, and so we can write phi of lambda as log determinant of y. So this y here comes from so the determinant of the product is the product of determinants, and then you can recombine these two square roots of a matrix and have this term here, and then you have basically this term. And what I will do is I will do eigen decomposition to this term multiplied by lambda, which is y to the -1/2, x minus y, y to the -1/2. Now, this quantity here, you can check that it is Hermitian. We have no idea whether it's positive, semi-definite or not. We do not really need this, right? But because like we have the difference between two positive definite matrices, who knows? Okay, but this eigen decomposition is valid. We just need the two matrices to be Hermitian. In that case, we get eigenvalues that are real valued, but we are not sure whether they are strictly positive or not. Not a problem. We do not need actually this quantity here to be positive definite. Okay, and so again we replace this identity by QQ Hermitian, and we replace y to the -1/2 x minus y times y to the -1/2 using its eigen decomposition because it's a Hermitian matrix. And then we do the same game again, right? So you can take this thing and say it's a determinant of Q, determinant of something here, and then determinant of Q Hermitian. So you take Q as a common factor to the left, Q Hermitian as a common factor to the right, and then you apply the property that the determinant of a product is the product of determinants, and then these two guys can be reunited as QQ Hermitian, and the Q matrix of the eigen decomposition of a Hermitian matrix is unitary. So QQ Hermitian is identity, and the determinant of identity is 1, and so you are left with the determinant of I plus lambda, and then the remaining guy here, which is this matrix. This is very nice because now we have a diagonal matrix, right? So basically, this is a diagonal matrix with ones on the main diagonal, and this is a diagonal matrix in which the main diagonal elements are lambda multiplied by, the eigenvalues of this matrix here. Okay, and so if we call those eigenvalues gamma, small gamma of 1, small gamma of 2, and so on, this is what we have. So this is our function phi of lambda. Okay, and we can show actually that that the thing that we have inside is guaranteed to be because x and y are positive definite, that basically 1 plus lambda gamma g is strictly positive. Now we want to check whether phi of lambda is convex or not, or concave. Perhaps it's concave. You have three possibilities: it's convex, or it's concave, or it's neither. And so it seems to be like, as a function of lambda, it seems to be a function that is differentiable. It is differentiable with respect to lambda. We just need to differentiate it twice. And here we will get a negative result indicating that phi itself is a concave function. And so basically the main function, the g function, which is the log determinant, is also concave. So we just do this. We take phi of lambda, differentiate it once. This is a constant. This part does not depend on lambda. And so we get this. 1 plus lambda gamma g. So here I assume that the logarithm is to the base e. Okay, so if I'm using like the MATLAB notation. If you don't write the base, it's like log is just len. Okay, it's so basically this is len, and so the derivative is 1 over 1 plus lambda. 1 over 1 plus lambda gamma g. And you are differentiating with respect to lambda, so you will have gamma j here, and then you differentiate another time, so you will get minus 1 over 1 plus lambda gamma j squared, and then you get an extra version of gamma j, and so this is positive. Okay, and basically this is positive. Okay, the sum here. So even if some gammas are 0, basically you are doing a summation. And basically, for x not equal to y, at least one of those gammas will be non-zero, and you get a negative value here. And so it means that your function is going. Even if we get a 0, I mean, we still have concave. I mean, this is strictly less than 0. I mean, if you want like to say, that the function is strictly concave. Okay, but in any case, this function is indeed concave. And because of what you learned in the tutorial session, that basically the phi function, what you say regarding it is applicable to the main function. Okay, and so log determinant of x when x is Hermitian and positive definite, this is a concave function. Okay, and I will give you later in the homework like other interesting functions involving variables that are arranged perhaps in a matrix form, and you can check whether the functions are convex or concave. Again, one of the tricks that should basically come to your mind whenever you deal with those apparently complicated functions is this trick, is to like scalarize the problem. Rather than dealing with a function in many variables, just use the phi function. It's a function of a single variable, and if it's twice differentiable, then checking whether it's convex or concave is relatively easy. Okay, any questions? Okay. So now what is the plan? We want basically, I mean, convex analysis is a big topic. Again, like you can spend a complete semester or two learning convex analysis and like the theory of optimization. So here I will be very selective, and the objective is that I want to basically prove the KKT conditions for optimization, and to do that I want to prove the Farkas lemma. So the Farkas lemma is the like sort of the intermediate step that is very important and is very useful whether you are talking about optimization or other stuff. So I think we will also use it when we study Markov chains. And so here I basically will select some results that are relevant to the objective. Okay. So first thing to define, so you have a subset of R to the n, and we want to define the distance of a point to this subset, which here I call the big S, and the projection onto that set, okay? So we take a subset of R to the n, and of course S itself is a set, again, that lives inside R to the n, and there is some point X. So we define a distance function, okay? I write it like this. So this is a point in the n-dimensional space, and this is some collection of points. I define the distance as the following. You compute the L2 norm of X minus basically each point inside S. Okay, so you go and compute the L2 norm of this difference, which is the Euclidean distance. You compute the Euclidean distance between X and each point in the set big S. And then the infimum is the distance. Okay, the infimum will be the distance. Okay, so here is how we define. So this is a definition. Okay, so we define the distance, again, from a point to some set, some collection of points living in the n-dimensional space as this, this basically, you obtain the distance to each point in the set, and then the infimum of those distances will be dx and s. Okay? Now, I will define basically the distance is an infimum of distances or L2 norms. So from the definition, you know that this is greater than or equal to 0. So question, when is the distance exactly equal to 0? So I will give this as a fact. The distance is 0 if and only if X is in the closure of S. Okay? So the closure of S, so basically what is the closure of S? So this is S itself and all its limit points. Okay, so you remember from your study of analysis that basically the limit points, so S contains points. You can obtain sequences from set S. For converging sequences, they converge to some limit point. Okay, this limit point may be in S itself or not. Okay, so you may say, okay, so S itself and all its limit points. So if you take a converging sequence in S, its limit point may not be in S. Yes, of course. So for example, S is equal to 0, 1. Okay, so that's a subset of R. Just and suppose that you have a sequence 1 over n. So that's a sequence of points living here, right? So basically this sequence lives in S. Each point in this sequence is in this interval. 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. And this sequence is converging, but it is converging to 0, which is not in this big S. So 0 is a limit point because there is a sequence in S converging to 0, but it is not in S itself. So for any set, you can get this set S bar, which is the closure of S, which simply means the following. You examine every converging sequence in S, and if you find that the converging sequence converges to a limit point that is not in S, you include it in this S bar, or the so-called closure of S. Okay, so S bar is S and all the limit points that happen to be not in S. And geometrically speaking, those limit points that, you can think of them as the boundary of S that is not part of S. Okay, like the point 0 in this simple example. So the distance is 0 if and only if X is in S or in the closure of S. Okay. By definition, what is the Euclidean projection of X? So again, we are talking now about Rn. What is the Euclidean projection of X onto a subset of Rn, which is this set S? The Euclidean projection, I will denote it as this big pi and X, S like this. So what is this set here? It is the set of points that are in big S and for which the distance between Z and the point X is exactly equal to the distance. Okay, and remember what was the distance? It's the infimum of, let's put here, W minus X for every W living in S. So what is the Euclidean projection? Okay, so let's go back to the definition of the distance. It has an infimum, not a minimum, because sometimes. Okay, so actually the better way is actually to give an example, a concrete example. Okay, suppose that your set S is a disk, an open disk. Okay, so S is living in the two-dimensional space. Okay, or let's call them x1 and x2, and x1 squared plus x2 squared is strictly less than 1. So what is this set here? It's those points. Right? So those are the points, okay? And so the boundary here is not included because you have, by definition, you define the set such that this is strictly less than 1. Suppose that your point X is here. Okay, so suppose that X is this point, which is 0, 2. What is the distance between this point and the set? What you will do, by the definition of the distance, you will measure basically the distance between this point and every point in the set itself. And then you take the infimum. So what is the distance between the point 0, 2 and, let's call this thing, say, S tilde. So the distance is 1. The distance is 1. But here is the question. Is there any element in S tilde such that the L2 norm of 0 and 2 minus Z, the element in S tilde, equals 1 exactly? Is there an element here? No, there is no element, right? You can get arbitrarily close to 1. Note the following, that the point 0, 1 is not in the set. Okay, so let's note it here. So the point here, this one, which is 0, 1, is not in S tilde by definition, right? By definition. Okay, so basically, it's like when you compute the distances, you get a set of values. Those set of values may not have a minimum. They are guaranteed to have an infimum. And so that's the definition of the distance basically has an infimum, but not a minimum, because basically the minimum may not exist. So in this scenario that I have here, you can find points in this set that are basically whose distance to x is very, 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 very close to 1. But there is no point with exactly with a Euclidean distance of 1. But you can get very close to 1. Okay? So let's go back to the notion of projection. So a projection, the projection is non-empty if you can find z in S such that the distance is, the distance between z and x is exactly equal to d of x and S. Okay, so again, this set may be empty. And here is the example. d of x and S is 1, but actually the distance between each point in this disk and the point 0, 2 is it's larger than 1. You can make it very close to 1, but you can never make it 1 for any point that is in the set itself. Okay? Theorem. If the set is non-empty and closed, then this, the so-called Euclidean projection of x onto S, is guaranteed to be non-empty. Okay, so of course, I mean, if S is empty, then this guy is empty, right? So this is sort of like trivial. If S itself is empty, then this set, the Euclidean projection, is empty. Okay, so we need S to be non-empty. But it is non-empty here, and the projection is empty. Oh, so you know what is the problem? The problem is that this set that I gave as an example, it's an open set in R2. However, if your set is non-empty and closed, then the projection, the Euclidean projection of x onto S, is non-empty in the sense that you can find an element in S such that the distance between x, if this element is called z, the distance between x and z is exactly equal to this infimum here. Let's prove this. So, the distance by definition is the infimum. Okay, from the definition of the infimum, there exists a sequence of points living in S. Let's basically have the sequence Z1, Z2, and so on, such that the limit of the distance between x and a number in the sequence, this distance in the limit as v tends to infinity is equal to ds x of S. So this is from definition, from the definition of infimum. Okay. Now, if this statement is true, it means what? So you have a function of v, limit v tends to infinity, some function of v, okay, is equal to something. By definition, it means that there is an n such that for every v greater than n, the distance can be made arbitrarily small. Arbitrary, challenge me with any positive epsilon, and I can find an index big N such that for every v greater than big N, this distance is less than the arbitrary epsilon. Okay, and so this is the definition of a limit. So again, from defining the distance as infimum, you can write down this limit, and from the definition of the limit, there exists an n such that for every v greater than n, this distance here this L2 norm of the difference between x and z sub v can be made less than the distance plus 1. Again, this comes from, if the absolute value is less than epsilon, this means that eta v minus L is less than epsilon and the greater than minus epsilon. And so basically eta v itself is living between L plus epsilon and L minus epsilon. Okay, so here what I'm saying that if this is the limit, then I can make this thing less than basically the distance, which is the limit here, plus 1. So here I am, I am using epsilon equals 1. You can use any number, by the way, and the argument will hold. Okay, I mean, then what? I mean, what's the idea here? Okay, so take this inequality, okay, which is true for every v greater than n. Here it is again. Then employ the reverse triangle inequality. So this L2 norm is greater than or equal to the L2 norm of ZV minus the L2 norm of X. So here apply the reverse triangle inequality, and now focus on this and this. Okay, so the L2 norm of ZV is less than D plus 1, and move this to the other side plus the L2 norm of X. And so this is true for every V that is greater than N. Again, what is the point? Okay, here is the point. So this distance, okay, it is some number, and the L2 norm of X is some finite number. It can be a huge number, but it is finite, plus 1. Okay, so this is some finite number. And this upper bound on the L2 norm of ZV is true for every V greater than big N. Okay? And so for every V greater than or equal to 1, we have an upper bound on the L2 norm of ZV, which is, what is the upper bound on the L2 norm? You go to vectors from Z1 to Zn and examine their L2 norms, and then you have this quantity here, which is an upper bound for every V greater than N, and it's also a finite quantity, and this is a finite set, so it has a maximum. It has a maximum that is less than infinity. This is an upper bound on the sequence. Moral of the story is that this sequence is a bounded sequence. The sequence here is a bounded sequence. Okay, so the first step, again, we want to show that if a set is non-empty and closed, then the Euclidean projection of point X onto S is a non-empty set. And so the first step is to use the definition of the distance using infimum and rewrite it as a limit, and then use the limit, the definition of the limit coupled with the reverse triangle inequality to show that each vector, or each point in this sequence, it has a bounded L2 norm. And so the sequence as a whole, we say that this is a bounded sequence. It means that, there is a bound on the L2 norm of E of any element in that sequence. And it's a matter of luck that in one single lecture we used the Bolzano-Weierstrass theorem twice. Again, a bounded sequence in a finite dimensional space means that there is a converging subsequence. Okay, and so those Z's, you can find the subsequence that is converging to something which is Z tilde. As a side note, I keep saying that the Bolzano-Weierstrass theorem, it's a theorem about bounded sequences in a finite dimensional space. Why I emphasize finite dimensional? Because actually the theorem does not hold in infinite dimensional space, okay? So this is a bounded sequence in a finite dimensional space in an infinite dimensional space. Consider a sequence, okay? So your first vector is 1 and then zeros to infinity. And then, I don't want to close, so this is an infinite dimensional vector, so it continues forever. And then another vector, which is 0, 1, 0, 0, 0, 0. And then another vector, which is 0, 0, 1, 0, 0, 0, 0. And then another vector, which is 0, 0, 0, 1, and so on. Okay, so what do you think about this sequence? Is it a bounded sequence? What is the L2 norm? What is the L2 norm of each vector that you see here? 1, just 1, right? So you basically, you take the squares of the elements. There is just one non-zero element, which is 1. So each of those vectors is indeed bounded. You know, each vector here has an L2 norm that is exactly equal to 1. In this sequence of vectors, is there a converging subsequence? Is there a converging subsequence? Can you extract a subsequence that is converging? What do you think? No. In fact, the distance between any two vectors is fixed at square root 2, right? If you take any of these two vectors, okay, so convergence means what? Convergence means that the distance between the vectors gets smaller and smaller and smaller. Okay, that's convergence. Okay, so now what is going on is that the distance between any two vectors here is fixed. It's a fixed number. You can never make it small. You can never make it small. Okay, you can never find a Cauchy sequence here in which the distance between basically successive element, vectors, or basically there is no point beyond which the distance between two vectors can be made arbitrarily small. The distance is stubborn. It is just square root 2. Take the difference between any two vectors and, you are stuck. So there is no converging subsequence. But actually those vectors are bounded, okay? So in an infinite dimensional space, you can find a bounded sequence from which you cannot extract a converging subsequence, okay? So it's just a point that is important, like, when you apply the Bolzano-Weierstrass theorem, it is for finite dimensional spaces, okay? So here we can find a converging subsequence, and this is a subsequence, okay, that is converging to Z tilde. Now, those are in S. So the subsequence itself is a sequence in S that is converging to a limit point. What does it mean that set S is a closed set? One definition of a set being closed is that the set contains all its limit points. So closed set. So it contains all its limit points. In other words, if there is a converging sequence to some point, this point is in the set. Otherwise, the set, you cannot call the set closed. You cannot say that the set is closed. So because the set, we are talking about here, by definition is closed, this limit must exist in the set. Okay, so Z tilde is in the set. Okay, consequently, okay, if you take the limit, okay, so this is something I did, like, so we can show, maybe this is a nice exercise, so nice exercise. I think it's just using the triangle inequality. You know that basically if we have this limit here, you can subtract x from both sides, and then you can take the L2 norm. So this will hold. So basically the limit of ZVK minus x, and then you take the L2 norm, okay, then so again, like the main result here is if limit some vectors, like let's say an n goes to infinity is equal to b, then limit n goes to infinity of the L2 norm between a minus another vector c is equal to b minus c. Okay, so you can show that this is generally true, and this is what I'm using here. Okay? So this limit is equal to the L2 norm of z tilde minus x. But this limit itself is equal to the distance. Why? Because we have this result here. So this result here, for the sequence ZV itself, this limit statement holds. And if there is a statement regarding a sequence, okay, so a limit, this holds for every V, then it holds for every subsequence. And so this limit, if you replace V by V sub K and take the limit as K goes to infinity, the limit will also be D of X and S. So on the one hand, the limit is this. On the other hand, the limit is that. And so these two must be the same. So we have theorems regarding the uniqueness of limit in standard topology, which is what we are doing here. A space like such as, R to the n equipped with the standard topology. So in this case, limits are unique. Okay, so we are not doing anything. So by standard topology, I need, what we typically do. I am not talking about anything fanciful. And in that case, if a sequence goes to a limit, and then you show that it goes to another limit, then it must be the same. So this is equal to Z. So there is a Z tilde in the set such that Z tilde minus X is exactly equal to this thing. So basically this set is non-empty. Okay, so this set is non-empty. Okay, so ideas from analysis. So everything here, if you think about it, basically we are using the definition of the set being closed. We are using, basically ideas regarding, regarding bounded sequences, that if we have bounded sequences in a finite dimensional space, then you can obtain a converging subsequence. So that's exactly the statement of the Bolzano-Weierstrass theorem, and so on. Okay, we are using the idea of the uniqueness of limit, that if you have, perhaps in an analysis or a calculus course, you took this exercise that if an converges to B, if an converges to C, show that B is equal to C. So basically this is the uniqueness of limit theorem, and it is what shows that, so you show that this is equal to that, and also it is equal to ds of x of s, then these two must be the same. So there is a point in S such that the distance between the point and x is exactly equal to this infimum. And so the Euclidean projection set is a non-empty set. Any question? So if set S is non-empty and is closed, we are sure that the Euclidean projection is non-empty. But does it contain more than one element? Yes, it can contain more than one element. Let me give you an example, right? So suppose that you have a set like this. So here again, let's call it again set 3 bar, which is greater than or equal to 1. Okay, so that's a set. Now take the origin. Okay, and so what is the distance between, what is this distance? It is equal to, okay, so you measure the distance between the origin and every point in this set, you take the infimum, so it is equal to 1. Are there points in the set that basically has a distance that is equal to 1? Yes, all those guys. Okay, so all those are in of the point 0, 0 and our set. However, if our set S is also convex, then actually this set is a singleton. It has just one element. Okay, so now we prove that. So the previous proof is that if S is non-empty and closed, then this set is non-empty. If S is non-empty and closed and convex, then this set is a singleton. It just has one element. Okay, here is the proof. Suppose that there are two elements in set S that basically satisfy their distances to X is exactly the distance which is the infimum of W in S of W minus X. Okay, and so if you have these 2 points, then basically both are in the Euclidean projection. Okay, our set now is convex. If a set is convex, okay, so if the set is convex, then any convex combination, right? So Z1 tilde is in S, Z2 tilde is in S, S is convex. So for every lambda Z1 tilde plus 1 minus lambda Z2 tilde is also in S. It's using the special case in which lambda is equal to 1/2, it must be true that 1/2 of Z1 tilde plus 1/2 of Z2 tilde is in S. The distance is the infimum. So definitely the distance is less than or equal to the distance between this point here and X itself. Now rewrite this as 1/2 of Z1 tilde minus X plus 1/2 Z2 tilde minus X. Apply the triangle inequality. You get this as an upper bound, but Z1 tilde minus X, it has an L to norm equal to the distance, and this one also is equal to the distance, and so this is equal to the distance. So you have a string of inequalities. So here we use the definition of distance, and here we use the triangle inequality. You started with this you ended with that. So it means that everything here is equal. So this is also equal to d of xs. Okay? Now, let's examine the L2 norm squared between these two guys. And you can check that it can be written in this funny form. Okay? It's not, you can just expand the right-hand side and convince yourself that you will get this left-hand side. Again, it's a nice exercise. What is this? This is d squared. What is this? This is d squared. Why are these two guys equal to d squared? Because we started with 2 points that are basically at a distance equal to d from x. Why did we do that? Because we assume that S is non-empty and closed, and from the previous page we are sure that there is at least 1 point satisfying this equation here. We assumed actually that we have 2 points, and now we are examining the distance between them. So this is d squared, this is d squared, and now what about this distance? So this is the distance between the midpoint between z1 tilde and z2 tilde and x. It's also d squared by this argument here, and here we exploited the fact that S is also convex. So these guys give you a 0. The L2 norm is 0, and any vector norm is 0 if and only if this is the all 0 vector, so z1 tilde is equal to z2. So it means that S has 1 element. It's a singleton. Okay, so that's nice. You add convexity to the mix, and now you know that the Euclidean projection is just 1 point in the set. Okay, if your set is non-empty and closed, you are sure that the Euclidean projection is a non-empty set. Now, if S is convex, then it is a non-empty set with exactly 1 element. Now, let's study a theorem. It's called the separation theorem. And I am calling it a separation theorem because there are basically several other versions, but here I will focus just on this one, which is relevant to what we are doing here. So S is non-empty, closed, and convex. Now you know what to conclude. If you read something like this, okay, then one element, okay. Now take X not in the closure of S. What is the conclusion? So you read a statement like this. What does it mean? What's the meaning that X is not in the closure? Anybody? It's not a limit point, okay, but more importantly, that the distance between X and S is strictly positive. Remember, so I give a fact at the beginning that if you have a set S and the point X, the distance, the distance by definition, it's defined in terms of the inferior of an L2 norm, so it can be 0, can be positive, and it's 0 if and only if X is in the closure. Okay, so if I say that X is not in the closure, it means that the distance is strictly positive. So if we have these two guys, then claim there exists a vector such that Y transpose Z, where Z is in S, is strictly greater than Y transpose X. And this is true for every Z in S. Okay, so you can rewrite this thing as Y transpose Z minus X is strictly positive for every Z in S. Okay. Okay, so let me, here it's like, this vector Y is like sort of abstract, but actually it has a geometric meaning. Okay, so let me draw you something here. So this is S, okay, and this is X, and here S is non-empty and closed and convex. So this point here, it is the Euclidean projection of X on S, and basically it's a single point because S is non-empty, closed, and convex. Okay, so let's call this thing Z tilde. Z tilde. Okay, so take the vector Z tilde minus X. So it is this vector. Okay. Now, what is vector Z minus X? So pick a point Z here. So that's a general point in the set. And take the vector Z minus X. A vector like this. Geometrically, I mean, if you think about like simple situations, basically, the inner product of these two vectors is always greater than 0. Okay, so Y is actually Z tilde minus X, as we will see. This inequality means that this angle, okay, theta, that theta is acute. It's an acute angle. Okay, so this is like the geometric interpretation of this result here. We will not, I mean, you do not actually need to do this, but of course, I know that some of you actually, like these types, actually, rather than the abstract statement. Yeah. So basically, this separation theorem can be understood geometrically. It tells you that if there is a point outside the convex set, and if you connect the vector from the point outside the convex set and its Euclidean projection, and then you connect the point outside the convex set to any other point in the set S, or even to its Euclidean projection, then the angle, the Euclidean, is the inner product. So here we are talking about like sort of the angle between these two vectors, because the inner product is just, you can write it as the product of the norms times cosine the angle. So basically the angle is acute. Okay. In an abstract way, we say that there exists a vector Y such that Y transpose Z is strictly greater than Y transpose X. Okay. How can we prove something like this? Z tilde. Okay, so Z tilde is the Euclidean projection. And so Z tilde minus, so the distance between Z tilde and X is equal to the distance. Okay, again, we are guaranteed to basically have this Z tilde and to have only one Z tilde because our set is non-empty, closed, and convex. Okay, and basically this is greater than 0 because x is not in the closure of S. Pick a point in S, Z, and because the set is convex, then a convex combination of Z and Z tilde will also be inside the set. And here I will prohibit lambda from being equal to 0. Okay? So in other words, that the meaning here that I'm excluding 0 is that Z is not Z tilde. Z is not equal to Z Z tilde. Okay? So big Z and basically take a point W that also is not, so also W is not Z tilde. Okay, but it can be very close to Z tilde. So we take here lambda, and lambda is not prohibited is not allowed to be 0, and you may guess why, because later we will divide by lambda, so we do not want it to be equal to 0. Okay, so we don't want our guys here to be Z tilde. Okay. The L2 norm squared of Z tilde minus X is less than or equal to the L2 norm squared of W minus X. Why? Why? By definition, because basically Z tilde is the Euclidean projection. So it is sort of the closest point in S to X. It's closer than any other point. Okay, so this inequality, so this L2 norm squared is less than basically the L2 norm squared of W minus X. Now take W and write it down using basically W is a convex combination of Z and Z tilde. Z is an arbitrary point in set S, and Z tilde is the Euclidean projection of X onto S. Okay, and so this is what we have. Expand. Okay, so basically expand the L2 norm squared. So you get the L2 norm squared of this term, the L2 norm squared of that term, and then you find the cross basically term, which is 2 lambda. Lambda is just a scalar, and then the inner product of Z minus Z tilde and Z tilde minus X. Okay, so we have this inequality, and so what you can do is this guy appears on both sides, so you can say by, and you have that lambda squared multiplied by this L2 norm squared plus 2 lambda, and then this inner product is greater than or equal to 0. Now we say that lambda can be anything but 0, so we can divide by basically 0 here and move this to the other side. So we will get that the inner product is greater than or equal to minus lambda over 2 the magnitude, the L2 norm squared of Z minus Z tilde. So we are dividing both sides by actually 2 lambda. Okay, so we are dividing both sides by 2 lambda. Okay, so that this 2 lambda goes out, becomes 1, and this lambda squared becomes minus lambda over 2 when this is moved to the other side. Okay. Okay. Now we will do this trick here, which is we will visit this bracket and rewrite it as Z minus X plus X minus Z tilde. Insert plus or minus X. Okay, and then when you do so, do the inner product. So you do the inner product of this with that, and then this with that. Okay, so you get Z tilde minus X, and this is what I will call Y. It's inner product of Y with Z minus X, and then Z tilde minus X plus multiplied by Z minus, sorry, I misspoke. Okay, so let me say it again. We have the inner product, so this thing here is equal to minus Z tilde minus X, which is exactly this thing here. So now we have minus the L2 norm squared of this vector. Move it to the other side. And so we have this inequality. We have this inequality. And this inequality is true for every Z. Yes? Okay. And for every lambda, we just need lambda to be not equal to 0. It can be anything else. Okay, so you stare at the right-hand side. I mean, can we make the right-hand side strictly positive? Okay, so you are given X, you are given its Euclidean projection, and you are given Z, right? So basically this L2 norm squared is a given number, and this L2 norm squared is a given number, right? So we are given X, Z tilde, and Z. The L2 norms are known. Okay, what can you control? You can control lambda, right? Lambda is a parameter that is positive. Okay, you can choose lambda to be small enough, right? So the idea here, if knowing those numbers, if you choose lambda to obey this expression, if you make lambda small enough, you will make the right-hand side strictly positive. Okay, so we are given those guys a small enough lambda makes the right-hand side strictly positive, and this is what we wanted to prove, that basically there exists a vector y such that y transpose multiplied by z minus x is strictly positive for every z in x. Okay, so I think here we do not need z to be not equal to z tilde. Okay, so this is not, it's here just only that that we prohibit w from being equal to z tilde by making lambda not equal to, but z, I mean, it will not harm the argument in any way. Okay, so this is a very important separation theorem, and again it's called the A-separation theorem because there are others that are relevant, you know, basically to optimization and that appear in convex analysis. This is what we'll need so that we can prove the Farkas lemma in the next lecture. Okay, so again, let's see the statement. You have a vector S, and basically you have you have a set S. It's non-empty and closed. So basically, it's non-empty and closed. So the Euclidean projection of any point onto S is non-empty. It's convex. So actually the Euclidean projection is a singleton. It's a set with just one element, which is Z tilde. Let's call it Z tilde. X is not in the closure, so the distance is strictly positive. So X is outside, you know, S. And you can show that you can find the vector y, specifically if you go into the details of the proof, this y is equal to z tilde minus x, such that y transpose z, so the inner product of y and any vector in S is strictly, and this is important, it's a strict inequality greater than y transpose x. In the next lecture, we will use this separation theorem to prove basically one very elegant result called the Farkas lemma.